Hello everyone, today we are going to examine the critical subject of metal extrusion defects in 5 minutes. I will try to keep the video as short as possible and try to touch on every topic. As engineers, we know that the success of an extrusion process isn't just about forcing a billet through a die. It is fundamentally about controlling metal flow. As we have seen, the way metal flows during the process has a massive influence on the final quality and properties of the product. When the flow is disrupted, or when process variables such as temperature, speed and friction are mismanaged, we encounter significant defects. Today, I will detail the three primary categories of extrusion defects: surface cracking, pipe, other known as fishtail, and internal cracking, often called chevron cracking. Let's begin with the exterior of the product, surface cracking. This defect typically manifests when the process gets too hot and too fast. Specifically, if the extrusion temperature, friction, or speed is too high, the surface temperature of the billet rises significantly. Thermodynamically, this excess heat weakens the material at the grain boundaries. Consequently, the cracks we see are often intergranular, meaning they occur along those grain boundaries rather than through the grains themselves. This is particularly common in aluminum, magnesium, and zinc alloys. However, there is a second mechanism for surface cracking that can occur even at lower temperatures. This happens due to the periodic sticking of the extruded part along the die land. As the material sticks and slips, it creates a surface defect resembling a bamboo stole, often referred to as the bamboo defect. To mitigate these issues, we must manage our process variables. The most effective solution is often lowering the billet temperature and the extrusion speed to keep surface generation within a safe thermal envelope. Next, we move on to the defect that affects the structural integrity of the billet's tail end, the pipe defect, which is where it gets the name fishtail. As you can see, it is shaped like a fishtail or a mermaid's tail, which one you prefer. Pipe occurs when surface oxides and impurities are drawn towards the center of the billet during the extrusion process. This essentially creates a funnel of impurities that enters the product. Parts containing this defect are structurally compromised and must be cut off as scrap, meaning they are worthless. This is largely a flow pattern issue. To minimize pipe, we have to encourage a more uniform flow pattern. We can achieve this by first, controlling friction and minimizing temperature gradients within the billet. Secondly, physical interventions such as machining the billet surface prior to extrusion to remove outer oxide layer. And thirdly, chemical etching the surface oxides before the process begins. If you realize this failure occurs mostly because of oxidization. So steps that prevent this oxidization really help prevent this defect. Finally, we arrive at perhaps the most insidious defect because it is often invisible from the outside, internal cracking, also known as chevron cracking. These cracks develop at the center of the extruded product. The mechanism here is similar to the necked region in a tensile test specimen, where hydrostatic tensile stresses tear the material apart internally. What makes chevron cracking fascinating is how heavily it relies on the geometry of the die and the friction involved. The tendency for this defect increases as you increase the die angle. A steeper angle creates more turbulence and stress at the center. It also increases if the material has a higher amount of impurities. But it might seem kind of counterintuitive. The tendency decreases if we increase the extrusion ratio and the friction. Well, you're gonna say the increasing the friction actually makes the outside crack more. Well, yeah. As engineers, it is our job to find the balance between these two values and optimize our friction values. In conclusion, we mentioned to stop surface cracking, we lower temperatures and speeds to prevent intergranular failure. Also, lowering the friction helps too. To stop pipe, we clean billet surfaces and manage uniform flow to keep oxides out of the center. And to stop chevron cracking, we lower die angles and increase the extrusion ratio to maintain internal compression. Thank you for listening. As a last note, I want to add, by understanding these detailed interactions, we can design better dies and processes.